My name is Muhd.Roszaiman bin Rosli. My metric number D2018108345. I will explain the answer for the question 1A from my group assignment. The question 1, compute the sum of the shaded area for each figure. We can see the figure is at the left side. We know the question 1, the area of the semicircle, which is 1/2 pi r power of 2. From the question, r is equal to 1. For the figure, I can make A stand for area to compute the sum of the shaded area for each figure is 1/2 bracket pi bracket power of 2 plus pi bracket power 1/2 power of 2 and so on. Okay, let's try test. If we make A1, we know R equal to 1. So we put to the normal formula. To answer A1, we got 1.5708. When we using form from the formula, from my form, we can see the answer is same. So I can say this is true. Okay, let's try the next form. What if the A2? We know A1 R equal to 1, so A2 will be R equal to 0.5. When we put to the formula, we get the answer A2 is equal to 1.3927, and when we using form, we also get the same answer. So this proof this is the right form. Okay, the next is when we go through, we get the final is equal to A equal to pi over 2 bracket 1 plus 1/4 plus 1/16 and so on, which means A equal to pi over 2 and R equal to 1/4. Okay, using the infinite geometry series, A bracket 1/1 minus R, which means A equal to pi over 2, R equal is 1/4. And we go through, and the final answer we get A equal to 2 pi over 3. This is the final.
Assalamualaikum, my name is Othman bin Muhammad. Now I will show you how to find the sum of shaded region in question 1b. First of all, we see the shape of the question is square, and the bottom of the length of the bottom square is 1. So the length of side is also 1. Now we see the inside of square shape is triangle. Now we must find the length of BD by using theorem Pythagoras, which is square root 1 square plus 1 square equal to square root 2. Now we know the length of BD. Now we must find BO. So to do that, BO equal square root 2 over 2, which is equal 1 over square root 2. Now we know the length of BO. Now we must find the area of BOC, which is 1 over 2 multiply 1 over square root 2 multiplied by 1 over square root 2. Now we can find the area of BOC is 1/4. Now we must find the length of O and O prime. So to do that, 1 over square root 2 over 2 equal 1/2 square root 2. After we found the length of O and O prime, we must find the area O, O prime and E. So 1/2 multiply 1/2 square root 2 multiply 1/2 square root 2, we got 1/16. Now we see the sequence is A1 equal area of BOC, which is 1/4, and A2 is area between O prime and E is 1/16. Now we must find the common ratio, which is A2 divided by A1, which is 1/16, divide 1/4, we get 1/4. The common ratio is 1/4, which is common ratio less than or equal 1, which means is convergent. So we can find the sum of area, which is geometric series is A over 1 minus common ratio. So 1/4 over 1 minus 1/4 equal 1/3. Now we got the sum of the area of shaded region here, which is 1/3.
Assalamualaikum warahmatullahi wabarakatuh. My name is SMN3023, metric number D201810829224. So I will represent my group to discuss about the assignments question 2A, which to find the general expression for the area AN from the figure of the square. Let us start to answer the questions. So here the length is given by 1 and width also by 1. So the total area for the square is 1 multiplied by 1, and we get 1 unit square here. So from the figure we denoted as A1 is half from the overall square, and A2 is half from the A1, and A3 is half from the A2, and A4 is half from the A3, and A5 is half from the A4, and A6 is half from the A5. Therefore, we write them as A1 is 1/2, A2 is 1/4, A3 is 1/8, A4 is 1/16, A5 is 1/32, and A6 is 1/64. So here, the series can be written as is n equals to 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 and plus so on. Because the total of these fractions or pattern will get 1. If we see the pattern here, we can see that the next term after term A1, after term A2 and so on, we can see that 1/4 is the product of 1/2 multiplied by 1/2, and 1/4 multiply 1/2, we get 1/8, and 1/8 multiplied by 2, we got 1/16, and 1/16 multiplied by 2, we got 1/32, and also when we multiply 1/2 with the 1/32, we get also 1/64. So since each successive term we can be obtained by multiplying the previous term by 1/2, so we denoted this series as the geometric series. So here, to find the common ratio, we divide each number in the sequence from the number preceding it. From an example, we divide A2 by A1. So 1/4 is divided by 1/2, and we get 1/2. So therefore R, which is the common ratio for the series, is 1/2. To conclude, the general expression for the area of AN, which is this one from the figure, is AN equals to 1/2 to the power of n, or we can also write as 1/2 to the power of n. That's all from me for the question 2A. Thank you.
Question 2B. What is this notation? In order to answer this question, we will define an infinite series and show how series related to sequences. We also define what it means for a series to converge or diverge. From previous answer in 2a, we have seen the general expression for the area AN. Well, an infinite series is a sum of infinitely many terms and is written in the form of this form, which is a sequence of an ordered set of terms. If we add the terms together, we get a series. Series sounds like it is the list of numbers, but it is actually when we add them together. As you can see, the denoted symbol of infinite series right here is just the same as the symbol asked by the question. So definitely the question is asking about infinite series. In other words, a series is the summation of a list of numbers or sequence. The n here is often called an index of summation or just index for short. Now, you might think it is impossible to work out the answer, but sometimes it can be done. Alright, using the series given from previous answer in 2a, we can find a finite sum of this series. So this is the series. 1 over 2 here represent the area of A1. 1 over 4 here represent the area of A2. 1 over 8 represent the area of A3, and the rest of the other terms here represent the area in the diagram. By adding the terms, it will give us the cumulative sums. For example here, 1 over 2 with 1 over 4. If we add 1 over 2 with 1 over 4, we will get 3 over 4. And if we add 1 over 8, we will get 7 over 8. 7 over 8 plus 1 over 16 equals to 15 over 16. 15 over 16 plus 1 over 32 equals to 31 over 32. And it happened continuously until the end of the series. If you realize, as the terms keep being added, the partial sums becomes closer to 1. To take a closer look, let us see in the form of table. Now, the first n here represent the terms 1 over 2 or 0.5 in decimal form. For the second n here is 1 over 2 plus 1 over 4, which equals to 0.75 or 3 over 4. And this process continue for the rest of the terms. As you can see, the value of the sum of first n terms become bigger and bigger as the n keep being added. On the 25th of the n, you can see the value here become closer to 1. Well, this definitely shows that when we add this sequence of an ordered set of terms together, we can get an infinite series. Well, another similar approach can be used to determine whether the general series has a sum by considering these partial sums. In general, we will get the same answer, which represent by this notation.
Now, let us see what is means for a series to convergent and divergent. For convergent, let's add the terms one at a time. When the sum of first n terms approaches a finite value, the series is said to be convergent. Based on the example we see on the left side of this slide, the sums are heading towards a value 1, so this series is convergent. The sums of first n terms is called a partial sum. So, more formally, we say it is a convergent series when the sequence of partial sums has a finite limit. For diverge, if the sums do not converge, the series is said to diverge. It can go to positive infinity, negative infinity, or just go up and down without settling on any value. Based on the example we see on the top of the right side of this slide, The sums are just getting larger and larger, not heading to any finite value. It does not converge, so it is divergent and heads to infinity. Next is geometric series. Geometric series is when the ratio between each term and the next is constant. We can see from the example on the right side of this slide, we can simply see that the ratio between each term and the next is constant. Next, telescoping series. A telescoping series is a summation where successive terms cancel each other out. From the example, we can see that this type of series can be easily calculated since all but a few terms are cancelled out. Lastly is harmonic series. The harmonic series has in the form of this. The harmonic series is a divergent.